Thermodynamics? Do I dare ask, did anybody just see that you just had to get a component of the mass velocity? Right, it's the same problem? Okay, good. Sound like a lot of you got that one. Good. Good. And the distance from the middle would be a quarter wavelength on the... Yeah? Good?
I'll see you next week.
Oh, good.
Had to throw a little eye in there.
All right. Hey, okay, well, I'll get us started here. Let me put these away in safekeeping here for the moment. And then what time we have left, which is about 50 minutes. Let's put closure to the chapter. Here's the game plan, just like before, is, as you know, last Thursday we did the beginning parts of this chapter. And we got one little section left. Actually, we got to kind of put closure to the thermal expansion that we had started, and I'll do that in just a second. And then the ideal gas law, and then we can get into examples. And we may or may not get to that today. My intent and my goal was to get started with examples then on Thursday, and so that we would have time for examples. That's why I tried to make sure we got started with this chapter even before we took that test. That was a big deal here, because I feel like these thermodynamic ones, you're going to want and appreciate the fact that we're not going nearly quite as fast as we did in those first 4 chapters. We did a chapter a day, and now we're going to do a chapter every other day. So let me remind you where we left off. When we left on Thursday, before you probably spent, a weekend talking about and thinking about waves, so it's probably been a while since you thought about the thermodynamics part of it, is we got started with thermal expansion. Just to draw your attention, you might remember that long rod I had out here and the little propane torch that I put on it, and we watched the dial move as it got bigger and smaller. And so what we left off with was the idea that if you took this rod and you heated it, the molecules inside would go faster and faster and faster, and then they would bump harder and harder, and they would need room. And so they would get a little bit longer. And so we would say there would be a delta L. And we said that length, how much bigger it got, was equal to some proportionality constant times the original length times the change in temperature. And that's where we stopped, and we emphasized that alpha in there was the coefficient of linear expansion. It was not the proportionality symbol that we started with at the first time. And so let's keep working on that for a moment. We could put in some numbers here. In fact, maybe it would be a good time to just kind of turn on the overhead and get started with that, because your book does make a long list of these thermal expansion coefficients. And if I pull this down, we can look at some of these. But probably the biggest thing I want to show you is just that this is listed in the table here in your book. And so as you do some problems, and then they ask you something like, you have a railroad and you are going to put down rails, how much room do you leave between the first rail and the second rail? How big is that gap? And so this is our expansion coefficient. And you can see things like aluminum expand quite a bit. I think aluminum's the most on here. Oh no, I guess lead's a little bit, a hair more here. But we've got aluminum and brass and bronze and copper and a whole list of things of how much bigger do they get. And that's kind of where I was hoping we had stopped. Actually, I was kind of hoping we had a chance to do one more step. Let's expand this a little bit here, because in reality, things aren't always built with a length. They're built with a length and a width. And so if something has length L and width W, what happens to its surface when you heat it? Okay, it's going to expand not only in its length, but also in its width, or I guess that's length, the way I got it labeled, and that's width. But it is going to get bigger. And so the surface area is going to get bigger. And how do you calculate that? Well, I guess I would start here by saying A for area, and I'll put nu, or when it is hot, is equal to what? Well, it would be the original length plus how much did it get bigger? The original width plus how much did the width get bigger? Fair enough? And so now it would be length times width. And if we put this idea of linear expansion in here, but we do it twice, it actually is a fairly simple problem. We get L plus alpha L delta T here. Here we get width plus, and then I'll just put alpha with delta T there. If we factor out an L from here and a width from here, we get 1 plus alpha delta T each time, and then we can square it. And in fact, I would write this as the area old, or the area when it was cold. And so this is the multiplication factor of how much did it get bigger. Maybe it's worth comparing it to the new length. If I said L new, that is L when it is hot, it would be the original plus how much did it grow, which would be the original 1 plus alpha delta T. So this 1 plus alpha delta T is a fraction, if you will. It is a measurement of how many times did it get bigger. And so notice when we're talking about a length, it's only to a power of 1. When we're talking about an area, it's a power of 3. Guess what will happen if we do volume? What do you think would happen if I took an object that had a length, well, maybe I should, well, I'll do width for height, what the heck, and then I'll do a D for depth or something. But if I have a three-dimensional object, what's going to happen when I warm that up? It's going to get longer in its length, it's going to get taller in its height or its width, and it's going to get deeper in its depth. And so all three dimensions grow here. And so the new box is going to be bigger. It's going to be taller and wider and deeper as I get there. And how would I calculate that new volume? In other words, by what factor did it grow by? And so I would say volume new, or maybe I should put volume when it's hot, would be L plus alpha L delta T. That's its new length. Its new width is W plus W, I'll put it in the same order, alpha W delta T. And its depth is D plus alpha D delta T. But again, looking at the same mathematics, I hope you will see that there's an L in here, there's a W in here, and there's a D in there. And so, once you factor each of those out, you get the same factor, 1 plus alpha delta T. Each one is growing by the same multiplication factor. So, this can be thought of what is the old volume, or the volume when it is cold. And so this is the additional factor. And I think you're seeing that, okay, that growth factor, if you will, to a power of 1 when we're just talking about length. This is the growth factor when we've got it squared. This is the growth factor then when we have it cubed. Now, your author even takes one step further and kind of does a simplification of this, an approximation, I guess I should say. If you come back and you look at the length, you could say, well, this alpha is really the key factor here, right? It's telling you how much did it get bigger for every temperature. I mean, the 1 here is telling you how much it already had. This next piece, which comes from this piece, is telling you how much bigger did it get, which is based on its length and its temperature change. And so that is what we called its linear coefficient. That was kind of the key recipe of saying how much bigger did it get. You just multiplied by those other two. Now the reason I point that out is we'll do the same thing when it comes to volume. We'll do the same thing when it comes to area, but we do it more with volume than we do with area. But whether it's area or where it's volume, watch this. What if I were to take the old or the cold volume and then multiply that out? What is a binomial cubed? What is a binomial squared? Well, I guess this would be old area. Maybe I'll start with the square one because you probably remember this one much easier. What is this squared? 1 plus 2 alpha delta t plus alpha squared delta t squared. And if you look closely at this, you will see that alpha squared compared to alpha, how big is this alpha? 10 to the minus 6. So if we square it, that's really small. So ignoring that part, then we can say that isn't this, that multiplication factor, equivalent to the linear coefficient? This would be the area coefficient. That is the number that if you wanted to know how much did the area increase, it would be 2 alpha times the original area delta t. Does that make sense? And so we would get an alpha for each direction. And so we can real quickly then calculate this is the increased in area. What would happen over here for volume? 1 plus all right, so it's 3. Maybe I better get this in the right order here. Alpha delta t. I guess I got to think myself. What is a Poisson's triangle here? Ah, there we go. 3. All right. Plus. Uh-oh, wait, I'm missing a factor, aren't I? I'm missing a square in here, aren't I? Oh, yeah. So 1 squared is 1. That goes away. And then that one squared. Then I would have a 3. And then I would have an alpha squared delta t squared. And then I would have a 1 alpha cubed delta t cubed. Again, kind of going through that same logic of any time we take alpha and we square it, or in this case alpha and we cube it, let's just kind of ignore those for a moment, then this is how much it is expanding in its volume. And so we could write then, just like we did over here and just like we did here, that the change in volume is 3 alpha times the original volume times delta t. And so our volume of our object will get bigger by 3 alpha. And so again, hopefully you see things will grow linearly, but they'll also grow in 3 dimensions. And so depending on what we want in the problem, we can look at how much did it grow in surface area? How much did it grow in volume? How much did it grow in length? All 3 of those answers are given by just this one linear coefficient. And that's my point. And that's all we'll need. If you come over here, your author does label volume expansion coefficients and calls it beta. And so if you would feel more comfortable then, we could write this as delta volume. How much did the volume grow? By saying it's beta V delta T. But that's just a long way of saying beta is 3 times alpha. And so we really don't need a column for beta if we have alpha. So you will notice none of those listed for beta are also listed for alpha. They don't need them. And in fact, the general practice, and it kind of makes sense, is that if they are solids, we just list the alpha. Because once we have the alpha, we can then figure out how much is its area going to expand by and how much is its volume going to expand by. On the other hand, think about liquids for a moment. Liquids just kind of flow around and fill up everything. And if you put them in a cylinder container like this, then they form a cylinder. If you put them in a cubic container, then they make a little cube. And so really what you're interested in terms of the liquids is how much did the volume change. It's whether it's a length or a width or a depth or all three. Kind of depends on what you poured the liquid into. And so the general practice is list all your liquids in terms of their volume will increase. If you so happened, which is, by the way, one of the homework problems, to pour your liquid into a very long, like a capillary tube in a thermometer, then you might think of it as just how much is it going to grow linearly. And in which case, take the beta and divide by 3. Right? And then you will get the alpha, and then you will know what its linear expansion coefficient is. And that's really the key to that homework problem, is to realize that, hey, they're going to give you, or you're going to look up the beta for, and I think that homework problem is mercury. I can't remember now if it's a mercury thermometer they tell you to work with or a alcohol thermometer. But either way, there's the beta, and then I can divide that by 3 to get alpha to answer the question, how much will the mercury expand when I warm it up 1 degree, and therefore how do I make this thermometer, and how far apart do I put the markings on the thermometer in order for it to read right, I think is the question at hand. And that's the homework that you'll be quickly working on. Well, as I said, that was the math for the expansion that I wish I had really gotten to on Thursday, so that we could do the very last part here. And the last part then is to say, let's look at gases in a little more detail. Because gases have something interesting here beyond just what the thermal expansion is. I mean, watch this for a moment, and let me kind of set the stage here. But one thing that you'll see with gases that we don't have that same option with our solids is if we go back to this little model and say, this is what a gas looks like, say, when it is cold. Well, what does it look like when it's hot? All right. So they move faster, they hit a little harder. Did you know it expanded? Right? I mean, they even have, look, the air. They can say here, look, the air at 0 degrees Celsius does expand. Right? But there's where you got to be a little bit careful, and could be a little misleading here, because it's true, it did expand. Watch, I'll start again. Here's cold. Here now is hot. What if I push on it? Can I make it smaller? And so the model of a gas does get more complicated, or at least one piece added to it, because we can't just really say, like in this chart, it's trying to indicate, hey, warm it up and it gets bigger. No, warm it up at the same pressure and it will get bigger. What if you push on it? Can you change the size of it? Yes. And so that's why it's very important, and the author makes a little footnote about this, that we look at gases in a little more complex way than just, hey, did they warm up? It's like, okay, did they warm up? But then what about the pressure? Did the pressure increase or decrease? Because that too can change its volume. And so it's not just temperature, but it's also how much you're squeezing it. Yeah.
So that's what that little sub A means. It's like at regular atmosphere.
Yeah, it depends on the type of process. What else do they say? Yeah, the last sentence there is the important part, right? At constant pressure.
I mean, but in the air, the little A, does that mean at like atmospheric pressure?
Oh no, that's the footnote that goes to here, and he's trying to give you a warning about things that are coming up. The first one is this. In the second sentence is probably the easier one. This is saying the gas is under a constant pressure, and that's what I was trying to show you with this kind of silly thing. Is push that down and say gases are a bit more complicated with that. And that makes them a lot more interesting, and we're going to do a lot of work with gases. And so in the next chapter you'll see this other warning he's kind of throwing in here, that it depends on how you warmed up the gas. And when I say that, you'll see next chapter we'll talk about what if you warm the gas so that its volume doesn't change? What if you warm it so that its pressure doesn't change? Or what if you warm it so that the internal energy inside doesn't change? And all of those get a slightly different result. And so we got to be careful as we start warming up our gases and how we do it. And that's really the takeaway lesson from here, is this is our first step to this. We got to be careful how we warmed up the gas. And so the author is saying, in this case, you can have a thermal expansion coefficient, yes, but you've got to be careful what we're talking about here. And here he's talking about constant pressure. And I want to go beyond that, which is going to give us the tools for any of the warming of the gas here. And so your author says, is there then a connection between the volume and its temperature? Well, yes, but there should also be a connection with its pressure. And so all three of them should fit together, and they do. In fact, it goes a little bit further than just those three. It goes to a fourth one, which is then how many molecules does it have? I like to kind of derive it this way. Your author says, let's start here with kind of a mental picture of this gas. If you take a box and you think of a bunch of molecules in there bouncing around, you could say, how much pressure is getting on those sidewalls? And since we don't have the most time in the world, and I want to make sure we do finish up this chapter, and then we'll get into some examples here, but if I were to start with it something like this, cold, and just have you look at that, I bet you can make a reasonably good guess here. What factors go into play on this pressure? And I think one of them shows up right away, which is, well, how fast are they moving? Right? I mean, what is the difference between something cold and something hot? How fast they are moving. So I would expect then that temperature to be related to pressure, but only on one of the temperature scales, which is on the Kelvin temperature scale. So when I put that up there, I am trying to say that pressure should be related to how fast they're moving, but only on the Kelvin scale. So there's one of my factors. I would put another in here that says it is probably equal to what I'll call the concentration. How about the number of atoms or molecules per volume? What kind of concentration do I have in here? And that's really what I want to get started with this conceptually. I mean, obviously there's a little bit of math, so maybe I shouldn't have said get started here. But as I look at this, I'm looking at this going, okay, as these bounce around, what is causing the pressure? What is pushing the styrofoam pieces up? And I hope you will see that, well, 1, how fast are they moving? 2, how concentrated are they? And that's what I'm trying to say up there. And so there must be some proportionality constant, which we are going to label as R here, and talk about that in just a moment here. But those are our 3, or maybe I should say 4 factors that fit together. I will put P for pressure. I will leave R alone. Number of atoms per volume. Yeah, so why don't I use V, since for a volume downstairs. What about the top? Number of atoms. Okay, and some of you will recognize this. I'm going to put a lowercase n. N is not really the number of atoms, it's the number of moles. Uh-oh. What is a mole? Yeah, it's a measurement for a large group. Think of it like a dozen. I mean, nobody probably questions that. If I said, go get 2 dozen donuts. How many donuts is that? Right? No, not a baker's dozen, just a real dozen. Right? 2 dozen donuts. Right? You would say, well, that's easy. A dozen is 12. I've got 2 of them. That's a total of 24. You didn't say go get 24, but I could, right? I mean, I could say n number of atoms. Or maybe I should say number of molecules floating around in there. Right? So again, I could say it either way. I could say go get me 24 donuts, or I could say go get 2 dozen donuts. I think mole throws students off because it's not quite as common. They're used to, you know, hey, here's a dozen cookies, here's a dozen donuts, here's a dozen whatever, right? Score. I can say, hey, go get me a score of donuts. Oh, not as familiar, right? 407 years ago, our founding fathers put, no. What's the score? Yeah, so some of you know it's 20s, right? If I said 3 weeks, how many days is that? Right? Well, you know a week is 7. So I'm trying to get the same thing. Whether you're familiar with the word or not familiar with the word, it represents just a number. And the mole does too. The mole, which we will label as N sub A, just represents a number. Don't make it harder than that. It's just a number. It's a grouping, but it's a big number. And maybe that's what makes it so hard. Because molecules are so small, Avogadro decided to put them together and say, okay, how are we going to arrange these? And as some of you already pointed out, Avogadro's number is a big number. It is 6.02 times 10 to the 23rd. So instead of saying, how many molecules do I have in here, I will say how many moles. Just like how many donuts do I have versus how many dozens of donuts do I have. Right? And so that's this whole idea. So with that said, the physics tells me how many atoms, but there's so many that I'm just going to label this not as the number of atoms, but the number of moles. So these should be connected, right? The number of atoms should then be the number of moles times the number in each mole. In the same way, if I asked you how many days were in 3 weeks, what would you do? Well, you just told me it was 3 weeks. How many days are in a week? 7. You multiply them together and got 21. And so that would be our connection between how many days and how many weeks, or how many donuts and how many dozen. And the same thing here. This will be our connection between how many atoms and how many moles of atoms. And so it's just a convenient number of grouping things together. We do it all the time in terms of weeks, in terms of months, in terms of dozen. And so we like to do that. And so that's how I will represent this next mathematical piece. And T for temperature, we've already done that. And so there is my mathematical equation. Many of you, I suspect, have already seen this since it's a very common ideal gas law. And you've probably seen it rearranged. I'll put it way over here so I can put a box around it. But if you move the V to the other side, then I think it might look a little more common to you. I just wanted to approach it a little bit different than I think many of you might have done in chemistry, and that's saying, where does this equation come from? What is the meaning behind this equation? And so let me just capture it in case you didn't. This is what it's saying. The pressure is caused by those molecules inside. And its numerical value then would depend on, one, how fast are they going, and two, what their concentration is, which their concentration you may think of as a third option. And so these are our four variables: pressure, volume, number of molecules, and the temperature interplay with each other. And so that is what we call the ideal gas law. How are those two connected, those four connected together? Which means then R must be the mathematical constant, right, that connects the units. And so we should ask, what units do we want to use for pressure? And so some of you, I hear you telling me atmospheres. Others, I hear you say pascals. And I'll put kilopascals in there because I heard that too. And we tend to use the pascals. And so that's probably what we will do 90% of the time. We will see atmosphere once in a while. But I think most of you have been exposed, if you've been exposed to this equation already, probably in terms of atmospheres. In fact, if I were to ask some of you what is the value of R, I bet you would have told me what? 0821. 0821 what? Yeah, an atmosphere times a liter divided by a mole divided by Kelvin. In other words, what you've already been exposed to was simply this: that if you take that value of R, you would need to put the number of molecules in what units? Moles. Sure. You would need to put your temperature in what unit? Kelvin. You would need to put your volume in what unit? Liters. And your answer for pressure would come out in atmospheres. So certainly nothing is wrong with that, other than we don't usually use atmospheres for our unit. So do not use that R 90% of the time. We also don't like to use liters for volume. It's redundant. What's, in my opinion, a much better way of dealing with volume? A meter by a meter by a meter. And a cubic meter. Now you could say, well, there's 1,000 liters in a cubic meter. Fine, but why be redundant? There's our volume. So for us, our useful value of R will be a little bit different. Instead of atmospheres, we will have pascals. Instead of liters, we will have cubic meters. We will still do moles. We will still do Kelvin. And if we do a unit conversion from atmospheres to Pascal and liters to cubic meters, you get 8.31. So don't be surprised if you're working on a problem, or in this case, you flip open the front cover and you look in here and it says, hey, what's the ideal gas constant? Oh, there it is. And it says 8.31. It does not say 0.0821. And that was kind of a little warning I wanted to give you guys from chemistry. You could certainly do it either way. Obviously, they are exactly the same, and I wanted to make sure you caught that. But this is the mathematical relationship between the pressure of the gas, the volume of the gas, the number of molecules we have, and the temperature of the gas. They are related by some factor R, some multiplication factor. And in this case, the 8.31 is our base units, and that's probably what we'll focus most of our time towards. Oh, let me keep going here, because we could write this slightly different, and we will eventually, not too much here at the beginning, but as you pointed out here, this N could be written in terms of how many molecules here. Let me do this. I could write this as PV equals, I'll just put the R and the T alone here for a moment. How could I get, say, the number of moles by knowing the number of atoms? Well, I guess it would be this relationship, right? I could write this as N divided by N sub A. N sub A being Avogadro's number, right? That's how many moles I would have. And in some sense, you will find this a much more useful equation. I know Boltzmann did, and so we will get there. We will start here and change it to what I would call more useful units here, or engineering units here. But I'll even take you one step further, because we will then stop using the R altogether and kind of group these two together. So help me out again. What was the R? 8.31. What was Avogadro's number? 6.02 times 10 to the minus 23rd. I'm sorry. Plus 23rd, and then I'm going to move it to the top, so it's going to become a minus 23rd in a second. Sorry. Yeah, so plus 23rd. And so this would be N, and then I would get the 8.31, 6.02 times 10 to the plus 23rd times T times P times V. And that number is our 1.38 times 10 to the minus 23rd. And that's, we will give the symbol K for constant, sub B in honor of Boltzmann. And so this is what we refer to as Boltzmann's constant. I should mention the units here. What would the units be? Well, help me out here. What would the 8.31 be in terms of units? Well, we just did it here, right? In fact, maybe I'll simplify this a little bit. What's that? Yeah, 2 of those upstairs cancel with 2 downstairs. So isn't that a Newton meter? Which is called a joule. So this is really a joule per mole Kelvin. Down here, this is the number of atoms, so it's just a number per mole. So we'll call it per mole. The per moles cancel off, and you get joules per Kelvin. And so Boltzmann's constant is 1.38 times 10 to the minus 23 joules per Kelvin. And so let me kind of help you along the way. This is going to be a much more advanced and useful way of thinking of the ideal gas law than probably what many of you have already been exposed to. So somewhere in either chemistry, either here in college or in high school, you probably were first exposed to this ideal gas law. And I suspect that your first exposure was just, well, here's the equation, here's the relationship, let's not worry about where it came from, let's just plug in the numbers. And that is a good place to start. I've got no problems with that. But let me take you one step further. Let's get away from these units and get to these units. Let's go even further. Let's get away from the mole and say, how many atoms is it? And we'll get down to this number that, as we're going to see, becomes very useful. And so I will add next to this PV equals to N K sub B T, and point out that these are the same. But this is really going to help us with our physics. This will allow us to think about the pressure and volume being related to how many molecules and this Boltzmann constant. I mean, let's look carefully. What is it really saying? And this is the first time you've seen it, but it is really something very important that is we're going to see throughout our thermodynamics. Is this number is saying how many joules do you get for every degree you warm up an atom. And so if you have one atom and it's at 20 degrees and you warm it up to 21 degrees, just that one atom, that's how much energy it takes. And that's going to be useful. We could look at this in terms of how much energy for every degree, for every atom. And we begin to see kind of a much more useful picture, as you will hopefully come across in our thermodynamics, that gets into the meaning behind Boltzmann's constant. So, as you will see, I like this form for the ideal gas law. This is a great one to get started and give you some insight. And it's a great one to do calculations with. Your author won't do much until next chapter, until we get to something like this. But they are interchangeable. So it all depends. Are you trying to look at a microscopic level? If you want to look at a microscopic level, this is a great way to do it. If you want to look at a macroscopic level, this is probably the way to do it. And if you want to deal with the energy involved, this is probably the better form of R, because R is in units of joules. And so you will see that sometimes we use this form and we use this constant to work out energy issues. Other times we use this form and we are looking at things on a more microscopic level. Seldom do we do this, but sometimes they give us things in atmospheres and liters, and so sometimes we will use that constant also. Question or just scratching? Fair enough. All right. But that's the very last step of this chapter. I could do an example or two, should I? Okay, good. I will. All right. I was afraid you guys might be too burnt out from the test. Oh, all right. But let's try a couple of these, and for today anyways, maybe I'll just do thermal expansion ones. I'll start with, say, number 10. It's been a long time since we've got a chance to actually do any examples for you. Now we're on a more leisurely pace, but that's what I'd like to see, is to say, let's go ahead and do some. Listen to this one here. It says, at 20 degrees Celsius, an aluminum ring has an inner diameter of 5.00000 centimeters. A brass rod has a diameter of 5.0500 centimeters. Can we fit the two together? So we have, in number 10, a ring where it says in here, this inner diameter, that number right there, is 5.0000 centimeters. And over here we have a brass rod And it has a diameter 5.050 centimeters. Can we fit them together? And obviously not in this situation, because the diameter of the brass rod is a little bit bigger than the hole in the ring. But how could we fix that? And that's what they said. If you warm only the ring, what must you warm it to in order to slip it over? And so if this is a construction process, this is part of the manufacturing process I alluded to last Thursday of moving parts together, we can warm up the ring, and as long as we go kind of quickly, we can move that ring, slide it across on the rod, and then place it where we want, and then once it cools down, it's going to get really tight around that. And so we are looking then at the option of changing the length or the opening of that ring by 0.05 centimeters or 0.0005 meters, right? That's the... now we could do area too, right? And if we do area, we need to look up alpha and double it. Or if we do length, we just need to look up alpha and not double it. So I'm going to do length here just to make it a little bit easier. But the real reason I picked this one is the same warning I gave you in class was, how do you deal with the expansion of a hole? The same as if there was material there. And so pretend, I know there's not really any material in this hole, but what makes up the hole is the material around it, and it's going to expand. And so that was the key lesson last time where you watched me do this. And so they are saying here that it's an aluminum ring and it is at 20 degrees. And so really what I want then is this thing to equal to alpha L delta T. And so 0.0005 meters is how much bigger I want the diameter to grow. The alpha I need to look up for aluminum. I had it on here, but I moved it up. I'm just going to grab it off the screen here. It was a 24 times 10 to the minus 6. Let me check the units. I'm pretty sure these are inverse Celsius there. And so that is my coefficient of linear expansion. My L is the 0.05000 meters, and actually I didn't even really need to convert to meters, I see now. And I was kind of suspecting that I would need to, but it looks like I don't need to. And then I'd get my delta T, and so there's the first half of the problem. What temperature? What temperature must you warm this up to in order for this to work? Thought I grabbed a calculator somewhere. And so if I try this, 0.123 and then a 5 divided by 24 times 10 to the negative 6. Divide that by 0.05, and I get a warming up of about 417 degrees Celsius. So I'm going to have to warm it quite a bit. But at least that'll get there. Maybe even a little hotter than that. Make sure it fits on real well and doesn't give me a chance to cool. And I can put those in there. But that would be the first part of the problem. How much would you warm it up? But let's say this. Here's the second part of the problem. What if you warmed up both? Could you warm up both? Now, I got to admit, why would you do it is a good question if you're just trying to assemble them together. In fact, if you're trying to assemble them together, it would make sense to warm up the ring and cool down the brass rod. And so that way you might not have to warm it as much. But let's say you put it in the wrong place. Can you reset it? How are you going to get it off now? And fortunately, the brass has a slightly smaller expansion coefficient. This is what it was for aluminum. For brass, it was only a 19 times 10 to the minus 6. So if you were to already have them put together and you decided it was done incorrectly and you needed to fix it, you could heat them up. And as you were heating them, they would both be getting bigger. But do they get bigger by the same rate? No, right? This, starting already bigger, is going to expand, but it's expanding at a smaller rate than the opening. So there could be a point, right, where it got hot enough that they become loose again. And so you can warm the two together. So if I say, what is my length? And I'll say new, and I'll say hot for the aluminum opening, it would be the original length, 0.05, plus alpha L delta T, 0.05, plus the alpha for aluminum, what do we say over there, was it 24? 24 times 10 to the minus 6, the original length is 0.05 delta T. So there's my size of my opening based on temperature. How about the new size when it is hot for the brass? Well, same idea. It's 505 or centimeters. So 0.505 is its original size. Then again, I would have an alpha times a 0.0505 delta T. Putting that number in for brass. Did I say it was a 19?
Yeah.
19. How are we doing on time? Uh-oh. Oh, we got till 5 after, right? Okay. Times 10 to the minus 6. And then 0.0505 delta T. And so, of course, they would have a different alpha because they're different materials. They would have a different starting length because that was, what they started with, different length. How about the delta T? Are these different delta T's? Yeah, not in this case, right? We're going to warm them up to some. Oh, which, by the way, I guess I should also emphasize before we run out of time, this is the change in temperature, right? They did say it started at 20. So you got to warm it up 417. So to get the final temperature, I guess I need to add 20 to that. So 437 degrees is really the answer they were after. How much do you have to warm it up to before it will fit on? Okay, starting at 20. Same thing here. These are delta T's, and so how much do we have to increase them by? But the neat thing about this is that we hopefully then mathematically can set them equal to each other, because that's the problem at hand. How warm do I have to go before they're the same size? And obviously you would suspect it's going to be more than that, since that was what it fit when you did not warm the brass at all. And so a little bit of math here. I'll subtract this, and this is 0.0005. I guess I need to subtract these two numbers. Why don't I just start, since I'm kind of short on time, I'll just plug this into the calculator. 24 times 10 to the minus 6 times 0.05 is 1.2 times 10 to the minus 6. Over here, 19 times 10 to the minus 6 times 0.0505 become 9.595 times 10 to the minus 7. So when I take the 1.2 times 10 to the negative 6 and I subtract that last answer I got, I get 2.405 times 10 to the minus 7 delta T, or finally delta T is 0.0005 divided by that last number, and I get 2,080 degrees. Which brings up a bigger question, which is, I think, why they put C. Is this physically possible? No, these are going to melt. I think aluminum's around 1,000 degrees C. I don't know. We can look it up here. But I think these metals are going to melt. So if you got them in the wrong place and they tighten up, they're stuck. You got to just melt the whole thing down and start again. Yeah.
When using alpha from that table, do we have to? It's starting at 20 degrees, right?
Right. Yeah, good point. And the table does make that very clear down in the bottom that these are values at 20 degrees Celsius. Yeah. All right. Well, we made a little bit of start here. More on Thursday.